Hello everyone, welcome, bonjour, bon dia. Welcome to this tutorial using B to program the CLEARSY Safety Platform organized within the conference ABZ 2021. We are on schedule, we have a heavy program, so we start just now. Two presenters today, Bruno Lavaux and myself, and 4 contributors. Bruno was involved in the certification and the development of the CLEARSY Safety Platform. Patrick Perron, who developed the educational version and the software simulator we'll see later on. And Lilian Birdie was responsible for some of the B models that we will see today. Most of the resources are available on our dedicated GitHub, CLEARSY period ABZ 2021. The objective today is not a course on B, it's not a course on the B method, it's more how to use formal method for serious things. So we have a large audience, students, teachers, researchers, engineers, and we would like to please everyone, and we will try to share as much as knowledge as possible. So you will require some understanding of formal logic, software development as well. And we will see all of these through a single example, railway level crossing. So many resources available. So the slides are available, not yet already, but almost. But you can also have access to the slides on the hands-on section on the right of your window. So normally you have a slide. At the moment you have the intro and part 1. I will release the 2 other slides set later on. You also have the programming handbook for the CLEARSY Safety Platform for education, and you have the installation procedure for the simulator. This tutorial will be available on YouTube this week. Just let me some time for the edition of the video. And other resources are available on GitHub, the source code and the formal models that are going to be demonstrated today. The CLEARSY Safety Platform for Education software simulator that is fully available right now, and also some informative PDFs. So the agenda is 2 hours. So we made another tray yesterday. It's 2 hours. It's full. So we have a lot of to say. The first part is introduction to safety, the level crossing example, and introduction to the CLEARSY Safety Platform, and then the presentation of the version for education and for industry, looking for this example deeper and deeper for the industry case, and at the end a conclusion. So what you can do during these 2 hours: listen, learn, browse the resources. Do not spend too much time on GitHub. So you have the slides, you have the documentation, you have the source code, and you have the models. You can play with the CLEARSY Safety Platform for education software version. You can ask questions on the chat anytime. So we will try to answer to most of them. So if it's quick, it will be answered on the fly or by batch during topic transition. In any case, if we don't have time to answer all the questions for any reason, you will receive answers collectively by email later on. So let's move to part 1. So the first part is about safety. So you probably know what safety means. It just means that the safety or the health of someone, the life or health of someone is at risk in case of failure. And when you design a safety system, you have not only to consider the safety objective, but the design of what you are going to produce, the environment in which it will be it's aimed to be executed or used. And once you have this design and idea, you need to implement it. And when you implement it, you need to consider that all the elements constituting the system may fail. And you should ensure that your system stays safe even with failures. And so at the end, you have to provide what we call a safety demonstration, that you need to demonstrate that there is always a risk, but the risks are kept below a threshold. So this is the story. And so we have different domains: trains, planes, cars, nuclear plants, etc. All these domains have specific standards, safety concepts, and so on. So, for example, the driverless trains are able to stop, but the planes can't stop in the sky. So you need to put the straits on availability and to have a human pilot able to handle complex situations. The cars, especially the autonomous cars, so-called autonomous cars, need to have a human driving assistant or safety assistant to take back the control of the car in certain situations, and for which the certification is yet not mandatory. And nuclear plants, where depending on the criticity of the functions, you just increase the number of barriers. So different domains, different approaches for the same notion. So the standards are just recommendations. So they are just industrial best practices. You don't have any receipt to produce a safe system. You don't have to follow a checklist saying, okay, do this and do this and do this. You have recommendation, and for all the stages of your development, you have what you can see on the table on the right. You have, depending on the safety integrity level, you have a number of techniques that you need to use, or it's so the R is for recommended and the HR is for highly recommended. So nothing is mandatory, if I remember well, or maybe one or two items. And in red, you have the formal and semi-formal methods. So you can use formal methods, but you can use any other combination of techniques to reach this goal. So the safety integrity levels represent the risk that you need to counter. And for example, when you're dealing with level 3, you owe to have one failure every century for one system, and level 4 is one failure every 10,000 years. So it's a very little number, but if you multiply the number of systems by this probability, you have a frequency of occurrence that could be quite often. The safety covers both hardware, software, and environment. So you have to consider specification errors, design errors, programming errors, bad compilation, long execution, failing hardware. So I remember I said anything may fail, even if when you program, you don't think about memory corruption, short circuit because there is a bug that is inside your computer, drifting clock, degrading microcircuit, and so on. Every failure that you can imagine might happen. And for this kind of architecture, for the highest safety level, you need to have several processes in parallel. So usually it's 2, but it can be more if you need more availability. Quite often you need 2 independent software development teams and independent testing team as well. And you need protecting mechanisms in case of perturbation. So you can't consider that everything is working well all the time. So in our example, the level crossing, so everyone knows about this because you need to take one of these every day or almost. The idea is not to prevent the train to stop. It's not to stop the train. It's just to prevent human beings to enter this dangerous area where the road and the tracks just crossing. And the idea is to make the driver aware of the situation. So you have the barriers just to prevent him from entering this area, and you have the red signal just to make him aware of the train approaching of the crossroad. So many different instances, depending on the countries, or depending on the technology, depending on the money. So you have level crossing with no barrier. You have single barriers. You have double barriers. Someone with delay just to allow the drivers to escape in case they were just stuck inside between the barriers. And there is no consensus about the position of the barrier. So in some countries, we have the barriers have to be open to consider the system safe, but in other countries, it's contrary. The barriers have to be closed. So okay, this is, and just to show you that is very. Yeah, P1. This is something that happened some years ago in France. So there is a truck that is stuck on the level crossing, and there is a train arriving, and you can see on the collision that the train is not in good shape. And the funny thing that you have people just recording on their smartphone, they almost die on the scene, but they try to record. Okay, so this is not something that we would like to avoid with our system, because in this case it's a fault, it's a driver fault. No, he didn't have to engage on this road. He had no room for it. Okay. So this is a view of the system. So it's simplified. So we consider trains going from left to right. So we have two cars, and so we have the road, we have the barriers that should be prevent drivers from entering the tracks when the train is approaching, and the train is detected to approach because we are using sensors. So they are called announcement pedal. So pedal is could be physical equipment. So when the wheel of the train move over this pedal, there is a contact, or it can be a magnetic sensor detecting the axle of the train. So you have an announcement pedal detecting the number of axles that are entering the area, and you have the freeing pedal at the exit. And you can see that if you count the number of axles, you can consider that the barrier is open when the number of axles between the two pedals is 0, and the barriers have to be down in case of a positive counter. So you have an engine to operate the barrier, and you have also a signal to warn the driver. So in our example, we are going to connect our sensors and actuators with the CLEARSY Safety Platform, so PLC that is being presented later on. And the CLEARSY Safety Platform is going to be connected to the outputs through relays, safety relays, because it's mandatory. You can't provide the energy. You can for the actuators. You can just switch on and off the current that is going through relays. So the sequence of events is as follows. An axle passes over the announcement pedal. So you have the red light flashes and the barrier is closed. Each time an axle passes over the pedal, the counter is incremented. Each time an axle passes over the freeing pedal, the axle counter is decremented. And after the last axle of the train has passed, so you have a counter is equal to 0, the red light go out and the barrier is open. It's straightforward. So a different view, decomposed. So before the train enters the area, the counter is equal to 0. So you have one axle going over the pedal. So the counter is going to 1, and the barriers start to close, and the light is flashing. And then you have a second axle, so the counter is now 2, the barriers are down. And then the train, so the freeing pedal is just after the barrier, because what you want is not to have drivers losing patience and going through the barriers, even if they are down. So you need to release the drivers as soon as possible. So the freeing pedal is just after the barrier. And so when the train has moved over this freeing barrier, the counter is equal to 0, and then the barrier is able to go up. So in our example, we have just decided it's our decision to consider that closed is safe. So the consequences for these decisions are the barrier engine I mentioned is used to keep the barrier open. And in case of power shortage, the gravity is used to lower the barrier. And in case of failing controller, because the controller may fail, the outputs for the engine and for the signals are off. So we should verify that the relays that we are using for controlling the engine do not provide energy in case of absence of command. So we have also a number of questions or subjects to consider. So we will not answer this question, but just to show that it's not only a question of algorithm that we'd like to formalize and implement. For example, what happened in case of negative counters? Is it possible to have more train access leaving the zone than entering? So many ideas. You can have trains going on the other direction. You can have faulty sensors. You can have a lot of possibilities, or you can switch on your system while there is a train in middle, and so you're getting negative counter. What to do in case of a train? Yeah, this is the situation. So you have a train between the pedals when the controller is switched on. So in case of power shortage, is it a problem to have a barrier going down while the signal is not on? What if someone blocks the barrier, preventing it to go down? And where to install the announcement pedal, meaning the distance between the announcement pedal and the crossing is quite important. If it's too close, the barriers do not have enough time to go down and the drivers to leave the zone. And if it's too long, the drivers will lose patience and just go through and risk to be collided by the train. So the global picture contains many things, many considerations, not just an algorithm to control this barrier, system, environment, procedures, traffic, human behavior, and so on. And so you have, when you go in this kind of system, you have to make a number of hypotheses just to restrict the number of situations you need to consider. So for this, we need a safety computer. So what is a safety computer? So a safety computer is a computer taking inputs, performing a transfer function F, and modifying outputs and iterating. Okay, and F is a special; it could harm and kill people. And a safety computer is a computer able to check if it is able to execute the function F properly. So it's a checkbox or the red cross, and to adapt accordingly. Accordingly means that if it's fit, just execute F, consume inputs and provide outputs, and if it's not fit, just do nothing and deactivate the outputs. And so what are these checkbox and red crosses? For example, red cross is if the memory is corrupted, meaning the data, the program, the register, if there is incorrect computation, meaning, for example, that your macro processor is not able to perform an addition in some situation. If you have an incorrect timing reference, so if you want to wait for 1 second and in fact the clock is going slowly, and you are not measuring 1 second but 10 seconds. So you need to be sure that your timing reference has some properties. And if you have some incorrect output physical status, so in case you are not able to command the outputs, so you can modify a variable in memory that is supposed to activate some actuator, but you are not able to modify the status. In this case, you need to be aware of the situation. And if everything is okay, well, if there is no problem, then you can go and you can execute F. And that verification involves both hardware and software. So some history about the CLEARSY Safety Platform. So it started in 2016 after 10 years of experience developing C4 system with PLCs. PLCs are automatons, so it's special computers, safety computers used in industry. So 2016, we started a R&D project called LSHIP, Low Cost High Integrity Platform. It was a collaborative project with the French Railways, SNCF. And we started to invent the CLEARSY Safety Platform for education. Following this, we organized a number of tutorials in Brazil. Thank you, Marcel, Valerio, for your help. In Canada, in France, Italy, Portugal, and UK. And we released the CLEARSY Safety Platform for education in 2019. And they are used as of today in university and engineering schools in France and Italy for master 2 classes. And at the same time, so it's a red part, some of the building blocks were used in systems that were certified in Brazil, in Sweden, and in North America. And from this, and when we got the CLEARSY Safety Platform ready for commercial, we started to invent the CLEARSY Safety Platform for industry, meaning just being able to use it for safety critical systems. And so it finished last year, and we got the certificate, SIL4 certificate for the core safety platform computer that we will see later on in January or March of February of this year, February. So what is the CLEARSY Safety Platform? It's a safety computer which implements the verification, your green checkbox and the red cross. The idea is to save time and to allow less expert engineers to develop, because as you can imagine, you have to consider a lot of aspects of your development and not just programming your algorithm. And one of the other specific of this approach is that we are using B, the B method, to obtain defect-free software, just to avoid a lot of testing. But there is no magic. So you need a software specification, of course. If your system study or design is incorrect, the safety is not ensured. If you decide to close the barrier, but in fact you need to open it, or to break a train or something similar, if the specification is incorrect, the safety is not ensured. You need to have some electronic skills for interfacing with the external world. And what is really important is F is not safe just because you are using a safety computer. It's not because it's safety ready that your function is doing right. And so the main summary for this is execute the right F and execute the F right. And this requires a lot of different skills for achieving this. So the main principle for the CLEARSY Safety Platform are F is a proof B formal model. This is one of the main aspects. The F code is generated automatically from the models. You have two identical microcontrollers to execute several diverse instances of F. So we have been asked several times, well, is there any need to have diverse microcontrollers? It's not required by our safety demonstration. We can afford to use the same microcontrollers to reach the highest safety level. And the power that is available is around 80 million instructions per second. And there is a continuous behavioral verification for this green and red thing. So the architecture starts from the F specification in whatever language, and the entry point for the compilation truth chain is B0. So B0 is the implementable part of the B language. So it can be obtained through a fully developed software in B. That is a preferred because, again, in this case, you avoid a lot of testing. Could be translated from a domain-specific language. I have an example to show in the next part. Or it can be directly handwritten, considering that B0 is very similar to ADA or to C without the notion of pointer. And then you have two chains generating for the same function two binaries to what we call replica, which during the execution they will compare their memory states, and they will check if they are doing exactly, they obtain the same results all the time. And they will also cross-check between the other microcontroller. So another view for the software architecture. So you have one main loop that is infinite loop, which executes F once a number of times. And at the same time, check the sanity. So check if the microcontroller is sane, and check if the other microcontroller is sane. So it computes this red checkbox and red cross thing. And at the same time, you have, so this is a sequential iterative behavior. And at the same time, you have interrupted behavior where you get the data and you control the outputs. So the main thing is we don't have any underlying operating system. So the main loop is executed as fast as possible, meaning there is no predefined cycle time. And the binary is made of two parts. So the replicated code, so you remember the two different branches for the code generation. And this replicated code is subject to what we call 2 out of 2 verification, and the non-replicated code. So the code is not executed and verified the same way. So we have two versions, version for education. So here you have blue boxes representing what has been developed or what is generated for you. So you don't have to modify or to write any of these things. You just have to concentrate on the green box. So to develop the function f as a B model only, so the replicated codes, most of the verifications are implemented. And we are using a cost-effective hardware interface just to lower the cost of the board, because it's for education. So we don't need to be as extreme as we are in the industry. And the counterpart cannot be used for real-life safety application because of this limitation. And so you have two versions. One is so we have the IDE plus the board, that is shown on the left. So you have 3 inputs, 3 digital inputs, digital meaning it's a 0, 1. So there is no continuous value, it's 0, 1, and 2 outputs. And you have the same thing with the board emulator, 3 inputs and 2 outputs. So I mentioned it at the beginning of my talk. It's you have a number of existing resources that have been experimenting in different occasions. We got a number of feedback. You have a handbook that is also available with the presentation of the programming model, presentation of the B language. We have some examples. Everything is available on GitHub as well. And you have the software emulator. So the software emulator has been released last week. So again, you can download it on the GitHub of the tutorial. So it's fully functional. And you can execute one replica, one, not the two. You can execute one replica of your application. So if you want to test it without having to buy, or you don't want to manipulate the wires and to connect your board with other equipment, you can go for this, and it's for free. And you have the version for industry. So the idea is to provide more flexibility at the cost or risk of errors, and you have to do more things. So here you have more green. So you can write the F function using B and C. You can program the sanity using existing libraries. You can program the main loop. You can program the data acquisition, the output counters. All the verifications are implemented, meaning that the product has been certified. So everything required is in the box. But you are, so the format is a smart card format, so it's quite small, and you need to connect it on the motherboard to get the power and to get access to input outputs. And so you can see on the right there is a starter kit motherboard with 32 inputs and 32 outputs, digital inputs and outputs. So you have a number of elements, technical elements. You have a library. The tool chain is Docker-based, so you just have to use your command and it compiles everything for you. It's more versatile, so you can program any kind of algorithm. You can do whatever with the interfaces you would like to. If you want to go for I-square, or I don't know, you can develop your own thing, electronic and software. So we have a certificate from Certifair that if you follow a number of conditions that will be presented by Bruno, in this case, it's quite easy to get your certificate. And it requires a motherboard for power and input outputs. Okay, so before jumping to part 2 and 3 for the one who want to stay with us, so again, it's not a course on B, it's not a course on formal method. We'd like just to demonstrate how to use these two things for education industry, using B, but also using C language and some bits of electronics on the level crossing controller. So 2 parts. The CLEARSY Safety Platform for education by myself, and for industry by Bruno.